So, welcome back to GOCC. Today we have Jasper speaking to us about matrix loci, orbit harmonics, and shadow play. Before we begin, let's go over a community statement. So, we are all learning, everyone has something to contribute, and no one has all the answers. So, with that, Jasper, take it away.
Okay. Thanks for the introduction. And yeah, I'm going to talk about matrix loci, orbit harmonics, and shadow play. And this is based on joint work with Yichen Ma, who just graduated from Cornell this year. Brendon, who's my advisor at UCSD, and Hai Zhu, who was an undergrad at Peking University. And he just joined UCSD for his PhD this year. So all these three words in the title may seem unfamiliar to you, but don't worry, we will start with something we are all actually more familiar with, and we will go over these objects one by one. So let's start with some basic constructions. So a partition of n is just a sequence of positive integers that are non-increasing that sum up to n. And we associate to a partition its Young diagram by putting here, as in the example, 4 boxes in the first row, and then 3 boxes in the second row, 2 in the third row, and so on. As many of you may already know, a standard Young tableau is just a filling of numbers 1 through n into the Young diagram for a partition like this, such that the numbers are increasing across each row and down each column. Okay, and maybe one of the most important bijections in algebraic combinatorics is the Schensted correspondence, which takes an element of the symmetric group and outputs a pair of standard Young tableau of the same shape. The Schensted correspondence is usually done using an insertion algorithm, which we will not go over here. But later we will see another way of doing the Schensted correspondence. There is okay, here is an example of a bijection. Here is a permutation in S8 in one-line notation. And the output, I just omitted all the boxes for simplicity. It's just this pair of scenario tableau. And we have one fact about this bijection is that if you look at the longest increasing subsequence in this one-line notation, like here, we can find the longest increasing subsequence is here and has length 4. So we write this of W to be the length of this longest increasing subsequence. One critical fact is that the length of the first row of this pair of tableau is equal to the length of this longest increasing subsequence. And the distribution of this longest increasing subsequence has been a pretty well-studied object. We write ANK to be number of permutations Sn with longest increasing subsequence of length k. There is a famous conjecture by Chen saying that this ANK is log concave. That means if you take the k minus 1's term and the k plus 1's term, take their product, it should be less than the square of the k's term. And we also have a result by Beck, Dyson, Johansen saying that this ANK will converge to a tracy rhythm distribution after rescaling and recentering if we put n going to infinity. So today's plan is that we will see a quotient ring which sort of knows this distribution of the ANK and sort of knows the Schensted correspondence. Here is our construction of this quotient ring. So we will have a n by n matrix of variables here, doubly indexed by 1 through n. And we consider the ideal generated by, well, the square of all variables, the product of any variables in the same row, the product of any variables in the same column, the sum of variables in the same row or same column. So the first impression on this ideal should be that it is homogeneous. So if you take the quotient, we will expect some grading on this quotient tree. The second thing is that if we consider the action of this metric group on the rows or the row indices I or the column indices J, we'll see that this collection of generators are stable under these actions. So that means we can have a two-sided action like Sn acting on one side and Sn acting on the other side. So we will expect some graded Sn cross Sn representation structure on this quotient tree. So to understand this quotient tree, we will need to introduce the Viennot shadow construction, which is the other way of doing the Schensted correspondence, as I mentioned earlier. The construction looks like this. If I have a permutation in one-line notation, I draw a diagram like this. So here in this permutation, 1 is going to 4. So I put a dot in here. So that means it's the first column and the fourth row. And 2 is going to 7, so it's here. 3 is going to 2, so it's here, and so on. And now imagine there's a light source on the bottom left that shines northeast, like this. And all the points will block everything to its top and to its right. So that means this entire region will be shaded, and we will draw the boundary of the shaded line here, and we'll call it the first shadow line. And then we'll remove everything on this first shadow line and repeat this process. So we can recover the second shadow line, the third shadow line, and maybe more. And the critical fact by Viennot is that the horizontal coordinates of these shadow lines are exactly the first row of the first tableau in the Schensted correspondence. So here is 1, 3, and 6. And the coordinates of these vertical shadow lines are just the first row of the second tableau in the Schensted correspondence. So 1, 2, 6 here. Okay. And we will take the northeast corners of these shadow lines, as in red here, and we'll call this point the shadow points. And the collection here of them, we will call them the shadow set. So recording the coordinates, and we have another fact, that is, if we just repeat this shadow construction on this shadow set, we can recover the second row of the pair of tableau. And if we iterate this process, we can just recover the pair of tableau in the Schensted correspondence. One more thing is that the size of this shadow set, because if you add the number of shadow points with the number of shadow lines, you should get all the n points. You should exactly get n. So that means the size of the shadow set is n minus the length of longest increasing subsequence of the permutation we started with. And given the shadow set, we will associate a monomial to it. So the shadow monomial is just the monomial that records the shadow set. So 3, 4, so x 3, 4. 4, 7, so x 4, 7. 5, 2, so x 5, 2, and so on. And the result by Brendon is that these shadow monomials becomes the basis of this quotient ring we first defined. And what's even better is the standard monomial basis with respect to the two-place order. So this is some result in Grosvenor theory, and two-place order is the lexicographic order with respect to the ordering of variables. So x11, then x21, and x12, and then x31, x22, x13, and so on, like this. All right, and this gives an immediate corollary that gives the Hilbert series of this quotient ring is just reversely labeled by A and K. Remember, A and K, it just counts number of permutations of n such that the longest increasing subsequence has length k. And recall that these are the generators of the ideal In. And we have that they are closed under the two-sided action of Sn. So the question we want to ask is, what is the graded representation structure of this quotient? This result was also originally answered by Brendon. That is, if we take the degree D part of this quotient ring, it can be viewed, it is isomorphic to a direct sum of irreducible reputations labeled by lambda tensor itself, subject to the constraint that lambda 1 is equal to n minus d. So because we're looking at a graded Sn cross Sn representation structure, you can think it like one copy of the Sn will act on the first irreducible representation, and another copy will act on the second one. And that's the story for this quotient ring. So these are some really nice and pretty neat results. But I guess a lot of you have this question right now. Where does this ideal actually come from? And short answer, it comes from orbit harmonics. So what is this orbit harmonics? Here is the setup. So if we have a sequence of variables and we take the polynomial ring of these variables, and we take a finite locus of points or a finite collection of points with some kind of symmetry in the complex vector space. As in the example here, we have a collection of 6 points that is stable under the action of S3 generated by these 3 reflections. What orbit harmonics will do is sort of it deforms it to a scheme of degree 6 centered at the origin. And algebraically, here's what's happening. If we have a finite locus of points, we can take I of z, which is the vanishing ideal of it. It's just the ideal containing all polynomials that vanish on all the points in z. And the classical result is that the coordinate ring is just the polynomial ring quotient by the vanishing ideal. Okay, and we will need to define this operator tau that is given a polynomial in the polynomial ring. Tau of f just takes the top degree homogeneous part of f. So here the top degree homogeneous part has degree 3. Tau of f just basically truncates this part. And if you have an ideal in a polynomial ring, its associated graded ideal is generated by tau of f for all f in this ideal. Okay. But one thing we need to be careful is that it's not necessarily true that if we pick any generator of I, and take the top degree homogeneous part of these generators will also generate associated graded ideal. It's not true. We need to actually be very careful when we think about the generators of this associated graded ideal. Okay. So the punchline for orbit harmonics is that we can extend this isomorphism of the coordinate ring and the polynomial ring quotient by the vanishing ideal by one more step. They are also isomorphic to the polynomial ring quotient by the associated graded ideal of the vanishing ideal. And we will call this last quotient R of C. And what's even better about orbital harmonics is that it's actually not just an isomorphism of vector spaces. This sequence of isomorphism will actually remember all the symmetries of this locus of point C. So that means if this C carries some group action, this sequence of isomorphism will be an isomorphism of the group representation. Okay. So yeah, another question you may want to ask is that why is this entire thing useful? So we will see a classical example in coinvariance theory and see how orbital harmonics will give us some results that may require more proofs in resulted. So we know that if we fix an integer, positive integer n, the ideal generated by the elementary symmetric functions of degree d less than or equal to n. So if we take the polynomial ring quotient by this ideal, we get the classical coinvariant ring. We know that it has dimension n factorial, and Chevrolet has the result that this quotient ring as an SN representation is isomorphic to the regular representation. So we will try to recover this result using orbital harmonics. Here is what will happen. We'll take our locus of points to be vertices of a permutation. Or in other words, we'll take our vertices to be just the one-line notations of permutations in Sn. From this construction, you can immediately see that the coordinate ring as an Sn representation is just the regular representation of Sn. So what? Now we will consider the vanishing ideal. The idea is for any d less than or equal to n, if we take the elementary symmetric function and subtract the elementary symmetric function evaluated on 1 through n, it will always lie in the vanishing ideal of these points. This is simply based on the fact that the elementary symmetric function is symmetric. So when we take the top degree homogeneous part of these polynomials, we'll just get the elementary symmetric functions. So that means this ideal we started with is contained in the associated graded ideal of the vanishing ideal of this locus of points, which is isomorphic to the regular representation. So with this, we can do an argument on dimension. So since I is contained in the associated graded ideal, well, then n factorial is equal to the dimension of the orbital harmonics quotient because we have this isomorphism. And it should be less than or equal to the dimension of the classical coinvariant ring because of this containment, right? This is this orbital harmonics quotient is quotient by this larger ideal, so it should have a smaller dimension. But we also know the coinvariant ring also has dimension n factorial, which forces these two to be actually equalities. That means the coinvariant ring is exactly the orbit harmonics quotient of the locus of points, which would then isomorphic to the regular representation. There are also other useful applications of orbit harmonics. So we have just in this one, we can get the classical coinvariance ring. Depending on the point locus we choose, we can also recover the Tanizaki quotient, the delta conjecture coinvariant ring, the rings with Donaldson-Thomas invariants, and also Garcia-Heyman module. So back to our topic, I want to explain to you how the idea we first saw came from. And we have already seen if we view our locus of points as permutations in one-line notation, but there are also other ways to view permutations. So our way is that we can view permutations as matrices. So Sn can be viewed as the collection of n by n 0, 1 matrices, such that there is exactly 1, 1 in each row and each column. Then we claim that with this setup, the ideal In we started with is exactly the associated graded ideal of the vanishing ideal of the locus of all permutations. So the idea of one inclusion is very straightforward. Is that the vanishing ideal will contain, well, here, this one basically says every entry is either a 0 or 1. This 2 basically says there is at most 1 in each row and each column. And this 2 says the row sum and column sum is always 1. So they will all vanish on the entire locus of permutations. So that means we have one inclusion of the ideal, because when you take the top degree homogeneous parts of these polynomials, we get the generators of In. So the proof idea is we write down this orbit harmonics isomorphism first and do the argument on dimension, similar to the result on classical coinvariance theory. Yeah, this one comes from the containment of ideals, and this one comes from that the shadow monomials will span this quotient. So that means all inequalities are equalities, and we have the equality of these two ideals. Okay, so this was the classical, the first result by Brendon. And after that, we asked the question, what other matrix loci can we consider? So the first thing I did was that we take the colored permutation. Algebraically, it's a Riesz product of the cyclic group of size R with the symmetric group. It can be viewed in one-line notation as an underlying permutation with a coloring of each entry in the one-line notation. The colors can be chosen from 0 to R minus 1. So R is the size of the cyclic group. But more, we can also view them in matrix form. So they can be viewed as n by n complex matrices with exactly 1 non-zero entry in each row and each column. And each non-zero entry is an rth root of unity. In here, so it's a third root of unity. Yeah, and to study these color permutations, we need to understand their irreducible representations and conjugacy classes. So the conjugacy classes are labeled by these R tuples of partitions that use upper indices to indicate each of them is a partition, and the total size of the partitions should equal to n. And the conjugacy classes, as well as the irreducible representations, of the colored permutations are labeled by just R tuples of partitions. So we can introduce this ideal, which is a generalized version of the ideal IN we first saw. It's generated by the R plus 1's power of each variable, the product of variables in the same row or same column, and the sum of R's powers of variables in the same row and same column. So if you put R equal to 1, the R color permutation is exactly the symmetric group when R is equal to 1. And we recover all the generators of the IN case if we put R equal to 1 here. And again, my theorem is that this ideal is exactly the associated graded ideal of the vanish ideal of the color permutation matrix loci. And again, one direction of the inclusion is straightforward. This one says every entry is either 0 or an R's root of unity, and similar for these other entries. And when I take the top degree homogeneous parts, I get the generators of the ideal INR. Okay, so to prove this, we need to also construct a basis for the quotient ring. And here is how it works. Given a color permutation, we write it in its one-line notation, that is, an underlying permutation with the colors. And here, since 1 is going to 7 with color 0, I'll just put 1, 7 in the color 0 part. And 2 is going to 3 with color 1, so I put 2, 3 in the color 1 part. And repeat this process. And now, I will do the shadow construction only on this color 0 set. And I will record the shadow set of the color 0 part. Now, as you see, I just omitted the color 0 part and replace it with this shadow set. And I will take a monomial that records the color 1 part, that records the color 2 part with a square. And eventually, when I reach the shadow set of the color 0 part, I will record it and modify it with an R's power. Okay.
Wait, I have a question.
Oh,
So
yeah.
for color 1 and 2, you don't use the shadow set.
No, just
Oh,
record it.
okay.
Yeah. Okay. And the theorem is that we have the equality of ideals, and these generalized shadow monomials we just defined here, they become a basis for the orbit harmonics quotient. That is they become a basis for the polynomial ring quotient by this ideal. And again, it's a standard monomial basis with respect to the same terminal order. Right. Yeah, the sketch is just first show that this generalized shadow monomial spans, and then we can use the similar argument on dimensions. I'll not go over this proof in detail. And from this construction, we can compute the Hilbert series. But this is a very sort of lengthy statistic. But if you rewrite it a bit, I'll just write it as CNRK, where CNRK counts this. Oops, what's going on? Yeah, CNRK counts this. We don't really need to fully understand what's going on here, but one thing to mention is that if I put R equal to 1 here, all these terms will be gone. And it's just counts number of longest permutations with longest increasing subsequence of length k. So in short, the CNRK is a generalized version of ANK, which counts a sort of generalized version of longest increasing subsequence in color permutations. And we were also pretty curious about what the distribution of the CNRK will look like. But somehow the log concavity actually fails in general. So for example, when r equal to 2, log concavity just fails for any n greater than or equal to 9. But we still do conjecture that the CNRK is unimodal. That is, it is monotone increasing up to a point and then become monotone decreasing. So this is just a picture of what the CNRK looks like when r is 2 and n is 40. As you can see, it looks like unimodal. And actually for the majority part, like say up to here maybe, it is log concave. But log concavity usually breaks down in either when like the case very small or very large. So this is what the distribution looks like. And similar to the SN case, we can let 2 copies of the color permutation act on the matrix of variables. And this will also induce an action on the polynomial ring quotient by these vanishing ideals, or the polynomial ring quotient by this orbit harmonics ideal. So we want to study this orbit harmonics quotient as SNR cross SNR representations. Here is the result. If we take the degree D part, it's isomorphic to a direct sum of irreducible representations. It's a direct sum of the endomorphisms of irreducible representations subject to this constraint. So R times the first part of lambda 0 plus the total size of the ith partition indexed and also scaled by I should equal to Rn minus D. And these endomorphisms can also be rewritten a bit. So it can be written as the irreducible representation labeled by these R tuples of partition lambda. Tensor the irreducible representation, or say the tensor the dual representation of this irreducible representation, which is labeled by lambda prime. Basically, it's fixing the first partition lambda 0 and reversing the order of all other partitions. And that is the story for the color permutations. And before we introduce our final object of study, I'll need to quickly go over some representation theory. So we have the ring of symmetric functions. And the Frobenius map is the map that takes an input and Sn representation and outputs a symmetric function. So if we put in the irreducible representation of Sn labeled by some partition lambda, the output is the Shor polynomial labeled by lambda. And there is also this notion of if we have a gridded representation, then there is a gridded Frobenius image that basically takes the Frobenius image of the degree D part and multiply it with q to the power of d. And the Frobenius image acts pretty nicely in this sense. So if you have a representation of Sn and a representation of Sm, their tensor product is naturally as an Sn cross Sm representation. And we introduce this induction product to be just the induction of this representation from Sn cross Sm to Sn plus m. So the nice property of this induction product is that if you take the Frobenius image, it will just be the product of Frobenius images. So this gives us some ease with computations. So our final two objects of study, the first one is what we call the matching locus, or I actually will always call it the involution locus. Here is why. What we have is actually the collection of involutions in Sn viewed as matrices. So the collection of involutions are just permutations such that in the cycle notation, all cycles has length 2 or 1. And why I call it matching locus is that this can, in this sense, so we have a 2 cycle, it can be viewed as just a matching between 1 and 4. So that means it can be also viewed as the collection of matchings on n vertices. And if you view them as involutions and in matrix form, they are symmetric permutation matrices. The other locus of points is the perfect matching locus, or I will also denote it as the fixed point free involution locus. So this happens only when n is an even number, and it consists of all permutations with only cycles of length 2. And in terms of matchings, they can be viewed as just perfect matchings on n vertices. And for matrices, they are just the symmetric permutation matrices with diagonal entries all 0. So we denote this perfect matching as PMN and matchings as MN. So the symmetric group can act on both locus of points by conjugation. The representation of the perfect matching locus is actually a known result. If you take the Frobenius image, it will be the placism of Sn over 2 and S2. We don't need to worry about what the placism actually is. The idea is it can be rewritten as a direct sum of irreducible representations labeled by lambda, satisfying all parts of lambda are even. So that means we can write it in this form. So the representation of the perfect matchings are just a direct sum of irreducible representations, all parts even. And now for the matching locus, we have the result that if we take the associated graded ideal of the vanish ideal, we'll have all the generators of the symmetric group case together with the symmetric differences xij minus xji. So as we have seen in previous results, one inclusion will be straightforward. And to prove this result, we also need to find a basis for this quotient. Here's what we'll do. If we have an involution, we will draw its the corresponding matching. And we will take the monomial, called the matching monomial, that records this matching. So 1 is matched with 4 because it's just a 2 cycle, 1, 4. I will just take the coefficient, I will just take x14 that records it. And similar for other cycles of length 2. Our theorem is that these monomials, matching monomials, becomes a vector space basis for the orbit harmonics quotient. And from this construction, we can directly compute the Hilbert series. So the degree D part, the degree D part has this form, the coefficient. Yep, this is what the coefficient will look like when n is 200. And we do have that this coefficient list is both log concave and top hat. And we also want to know the graded structure, and the result looks like this. If we look at the degree D part of this orbit harmonics quotient corresponding to involutions, the Frobenius image will be SD bracket S2, this is a plastism, times the Schur function corresponding to the one-part partition of size n minus 2D. And I will show you how where this one came from. So the degree D part from our construction corresponds to matchings of D matched pairs. So we consider actually two representations of smaller symmetric groups. So this one corresponds to perfect matchings of 2D vertices. And this part is just n minus 2D isolated vertices. So the fact is that the degree D part of the orbit harmonics quotient corresponding to the involution locus will be the induction product of these two, which is just matching some n vertices with exactly D meshed pairs. So that, well, recall that this one we have seen has Frobenius image as the bracket S2, the plastism. And this part is just the trivial representation, which is as n minus 2D. When I take the induction product, I just take the product of the symmetric group. Sorry, of the symmetric functions. And that's the story for the involution case. For the fixed point free involution locus case, the associated graded ideal for the vanishing ideal, we just add in all the diagonal entries xi to the previous case. We also have that we can directly compute that the graded Frobenius image looks like this. So it's a sum of irreducible representations labeled by lambda, but all parts of lambda are even, and the grading is determined reversely by the length of the first part of lambda. This is equivalent to saying this degree D part is a direct sum of irreducible representations labeled by lambda, satisfying all parts of lambda are even, and lambda 1 is equal to n minus 2D. But this time we did not find a basis for this quotient ring, and this proof only uses representation theory. Yeah, the corollary can be computed. That is, if we look at the Hilbert series, it's sort of reversely counted by the length of the longest decreasing subsequence of the permutations. The fixed point free involutions. Yeah, and this result only uses properties of the Schensted correspondence. And we also care about the distribution. Here is what it will look like when n is 100. And Bike and Friends has the result that if we let n go to infinity, these coefficients will converge to another trace-rhythm distribution after rescaling and recentering. Okay. And there is another result by fixed points, which we actually know the least about. If we take matchings or involutions with exactly A fixed points, the graded Frobenius image will look like this. So it's a very lengthy and messy formula, which we do not understand very well. The idea is if we take these two are consecutive terms in the graded Frobenius image for the involution locus, we'll need to take the difference and truncate it by the length of the first part of the partition. So it's we actually understand the least about this one, and I will not go into details of what this one actually means. And I will conclude with some possible future directions. The first one is we are curious what this coefficient list of the Hilbert series of the color permutation group looks like when we apply the orbit harmonics method. Here is what the distribution looks like. From this graph, I think we can be pretty confident that will converge to something. And this should be something pretty nice, but I don't really know how to do it. And yeah, we are also curious how we can find bases for the perfect matching locus in the orbit harmonic setup. And again, the basis we found for the evolution locus is not a standard monomial basis system anymore. It's just a vector space basis. So the standard monomial basis theory is also quite interesting. There's also this notion of equivariant log concave. So if you have a gridded group representation, we call it equivariant log concave if we have an injection from the degree d minus 1 part tensor the d plus 1 part to the degree d part tensor itself that commutes with the action of the group. So this will actually, if this holds true, then it will actually imply the log concavity of the Hilbert series. So Brendon gave the original conjecture that the orbit harmonics quotient ring from the symmetric group is Sn cross Sn equivariant log concave. So this is a very strong conjecture and will actually imply Chen's conjecture if proven. And we also have the conjecture that if we take the evolution locus and the fixed point free evolution locus, the quotient rings from the orbit harmonics are Sn equivariant log concave. And lastly, there are other matrix loci that can be considered. For example, a general complex reflection group, or another or Weyl groups of specific types, and other cycle types in the symmetric group, including maybe one big cycles or derangement and other stuff. And there is also a recent result on contingency tables by Jason O and Brendon that relates contingency tables with its zigzags. And there is also a current project going on that generalizes this result to the collection of all loop placements. And that is all. Thank you.
Thank you. Oh, people are clapping. Does anyone have any questions for Jasper?
I can ask one. Nice talk, Jasper. I was wondering if you had looked at like the Macaulay inverse system to any of these. Like I think sometimes when you do orbit harmonics, things get interesting when you like take the perp space.
Yeah, that's a
Different
really nice
approaches.
question. Short answer is that we did not look at them because as you see, all the results are mainly like the more algebraic, but something interesting might actually show up if you look at that, but we just haven't done it yet. Yeah.
Cool.
I see. But you haven't looked at it at all. Like you don't have a hunch whether like you would have a nice description in terms of the inverse system.
No, not really.
Okay.
If we have that insight, yeah.
hmm Yeah, I guess what my question is about this monomial basis question we have right here.
Mhm.
Like what are like the obstacles you face when you try to like apply normal standard monomial basis theory
Oh
to
yeah, good question. So the thing is, for this matching locus here, our construction was actually more straightforward compared to the shadow construction, right? So shadow construction, you need to actually do the Viennot shadow setup, but here we actually just take the monomial that
Yeah.
reports the matching.
Hmm.
So the thing, what happened here is like we had an intuition that this matching, this will become a basis. So we just worked with it and it worked out. We do have a conjecture on what the standard monomial basis will look like. It also relates to the shadow construction, but you need to sort of like truncate the extra terms because we have these generators here. So you need to sort of do some truncation on the shadow sets and then it becomes the standard monomial basis. But we don't really have a proof for that. That's where we got stuck on.
I see. And because you had this nice description of this other basis, you're like, oh, we don't actually
Yeah,
need
it will be, it's useful, so we just adopted it, and it's like a pretty nice one. So
I see. That makes sense. Do you have any idea whether these monomials you have here are like leading terms with respect to some other order?
it's possible, but we don't have an idea of what that order may look like.
Okay. Do you have any more questions for Jasper? If not, I can pause or can stop the recording. Let's see. Or I guess maybe I ask Bailey to stop the recording.